Okay, so we're going to switch topics a little bit, although Anne mentioned parameter estimation just about half an hour ago. So that's what we're going to talk about now. Parameter estimation is actually one of the most used features of COPASI. It's when we analyze the papers that use COPASI and that have use many of its functionalities, we always look for what did people do, and I would say probably 85% of the times they're doing parameter estimation. Sometimes with something else, sometimes just doing parameter estimation. So normally, I mean, so far we've been mostly talking about what in this kind of busy diagram I call forward modeling. That's going from a model together with parameter values and generating a simulation. That's really what we normally call simulation. But often what you do have is a set of experimental data that you want to use, and you want to adapt your model to represent those data in a way that makes sense. So you want your model to behave like the experimental data. And that's what we call inverse modeling, which is comparing a model behavior with experimental data and eventually tuning the model, basically going around this cycle, tuning the model to make it look as much as possible like the experimental data that was measured. Now, you can measure it yourself, or you can have obtained it from other groups through collaborations or published data, etc. But this is often something we want to do. And as you have seen, COPASI can do it, and Virtual Cell can do it as well, using some of the COPASI routines. So I just want to talk a little bit more about it, about all the different aspects of parameter estimation, things that are important, how these things play around together, etc. So first of all, let's formalize this parameter estimation a little bit. Let's describe the problem formally. And essentially, given a set of data, we want to adjust the parameters of a model to minimize the distance between the model and the data set. So as you can see from this language already, the word minimizing appears. It's to make the distance as small as possible. And essentially, we're going to apply numerical optimization algorithms and try and essentially automating this process of changing the model to make it as close as possible to the data. And there's many ways of doing parameter estimation. You can minimize some kind of a distance metric. You can maximize a likelihood, etc. But invariably, this is an optimization process. We are going to do minimization of a distance. Essentially, it's the least squares approach, which in a certain way can be formalized, can be described as minimizing the Euclidean distance between a model and the data. There are other ways that statisticians can enumerate, can describe least squares parameter estimation, but this one, I think it's kind of intuitive. So essentially what we have is a set of data, which are like these dots here, these red dots. And our model, which is a continuous line, we can measure the distance between the model and the data by measuring these vertical displacements between the model line and the data line. And each of these segments is called a residual, that is the model minus the data, which can be positive or negative. And we want to minimize the sum of the squares of these residuals. And why do we do the squares? Because we want the total to be smallest as possible. So if we minimize the square, we're taking out the sign, because we don't want the negatives and the positives to be different. We really want to be as close as possible. This could have been done with a different metric. It could have been done with the absolute value. That, unfortunately, it's a non-continuous function. The square function is better because it's a parabola, so it's continuous and in principle smooth if the data points would be smooth. So we are going to how can we do this? How can we make the model approximate the data? Well, the model depends on a number of parameters, which we have been talking about. And by changing those parameters, we can tune the model more or less closer to certain data points. And that's exactly what the whole principle of parameter estimation is. So in this mathematical enunciation, this f of x and k is the model. The vector of x's is the set of data. So those are the observables. Those are the things that were measured, which are also the variables of our model, or some of the variables of our model, and which we will call dependent values. And why are they dependent? Because they have to, in the model, they have to be calculated based on the equations and the parameter values. They are calculated values, so they're dependent on the equations and the parameters. Then finally, the parameters themselves, they are independent in the model. We set any value we want for a parameter. Of course, we want a value that approximates the model as best as possible, but they are normally called independent values. This terminology is important, as you will see later on. Now, when we do parameter estimation, we have to be careful with, particularly when we are fitting more than one variable. Let's say that you made measurements of two different chemical species, and one of them is in nanomolar and the other one is in micromolar. Well, you have to take care about the difference in scales, because if you're going to sum all the residuals, all the differences between the model and the data, the distance between the model and the nanomolar variable is probably much smaller distances than the distance between the model and the variable that's in micromolar. Probably around, on average, probably around 1,000 times larger, right? Intuitively, at least. Well, may or may not be the case. But in general, if a variable has a larger value, then the residuals will be larger. For the same percentage error, the residual will be larger. So we have to be careful with that, because the sum of squares, so the sum of squares need to be adjusted. So what we're going to do is we're going to weigh the data. We're going to apply some scaling factors to some of the variables, both in the measurements and the model, of course, because we have to make the model look like the measurements. And they will rescale the variables just so all the variables have a similar contribution to the sum of squares. So just to give a little bit more of an example, if you see we have, this may even be the same variable. Maybe we have different experiments where we're measuring one variable, and in some experiments it's in tenths of micromolar, and in the other one it's 100 micromolar. So it's the same variable, but it's different concentrations. So the errors are going to be different. And this is what this figure demonstrates, is that this variable is being measured here in different, the scale is different, as you can see, and therefore, if we were just using the data as it is, then this experiment would be fit because it has the largest residuals. But then this experiment would probably not be fit because it has very small residuals compared with those. And so the optimization algorithms would minimize the distance here, and those random errors probably would contribute very little and therefore would not be fit. If we scale our data to the same scale, then all of them contribute more or less equally, and that's what we want to do. And as you will see, there's different ways of scaling the data in COPASI. So this was just to say that we're using optimization algorithms. Basically, we are minimizing functions. I think this is all I want to say about this slide, not a lot more. If we were talking about optimization, I would go deeper into this, but right now, just bear in mind that we want to find, ideally, the global minimum of a function, the lowest possible value. Now, if a function is like this, which is very possibly the case because the measured data has inherent error, we don't want to end up in this place. We want to end up there because that's a much better fit than this one. So ideally, we would like to have a global minimum. And maybe we will see an example where sometimes you don't get the global minimum. Now, all the optimization algorithms work according to the same principle, which is they start with a certain initial parameter guess. There is a set of values of parameters that could even be random, but or it could be your best guess, but they're certainly a guess. They're likely not close to the solution. We use them to simulate the model, and we compare the model to the data and ask the question, is this close enough? We're going to have a criterion to know when is it close enough. And if it's close enough, that's it. We've solved our problem. We can end here. If it's not close enough, then we move on to another procedure, which is changing the parameter values. And this is where all the algorithms are different. This is where the optimization algorithms sit, and they have different methods by which they change these values, but they do. And again, we evaluate the function with the new parameter values, and we measure the distance to the data. And if we're satisfied, we stop. And if we're not, we go again and change the parameter values. And hopefully this will start getting the error smaller, and at some point we converge to a solution. This is how all the algorithms work. Some of them do crazy things like finding parameters at random, just drawing random numbers for the parameters. Others use things like gradients of a function, derivatives, etc., to try and guide us to the direction towards where the model wants to be. But apart from this particular, the particulars of each algorithm, the entire process is always the same. So we could generalize it in COPASI. And because of that, we were able to add many different algorithms. Here are just a number of algorithms. They're of different nature, and I don't have time to explain exactly how these algorithms work. But bear in mind that this group here is essentially based on derivatives. It's based on calculus, trying to find the minimum of a function by going down in the gradient. These here are more or less geometric algorithms. They try to find directions using some kind of geometric type of algorithm of where down should be, where downwards should be, not by calculating derivatives, but by other types of considerations. These algorithms mimic natural evolution, so they create populations of solutions, of guess solutions, and they combine them and recombine them in ways similar to how populations of animals and plants mate and create new individuals, which eventually, after many generations, become very, very optimized towards their environment. So here's the same thing, except now we're applying the laws of genetics or population genetics to populations of guess solutions. And then there's other algorithms, mostly stochastic, but based on, or some of them are also based on natural processes such as simulated annealing, which mimics how crystals form. Crystals are basically structures at minimum of energy, so they mimic how a crystal is formed in terms of these algorithms, or particle swarm, which is also a very useful algorithm that mimics how groups of animals, of social animals, find solutions to their problems in a cooperative way, such as ants looking for food and communicating with each other, or birds flying in a flock and not exactly knowing where they're going, but more or less all working by communicating with each other, essentially. So the ones that I highlight here are algorithms that normally give good answers, but as you will see, this isn't always the case, and you have to try more than one. So this will be the first thing to say, is that you need to try several algorithms with your problem to find out at least the best you can. Now, when we do parameter estimation, we can apply it to data that was obtained from time course measurements. That is where there was some perturbation and one followed a concentration or a absorbance or a fluorescence of some molecule. Or they could be observations of a steady state, a system which has relaxed and is already kind of in a resting state. And in COPASI, you can actually combine measurements from time course experiments with measurements from steady state experiments. So we're going to start by fitting time course experiments. Basically, the characteristic is that on the x-axis, we're always going to have time, and the y-axis is a measurement of one of the variables, and then we may have several variables. As in this case here, this model has 3 variables that will be fit in several time points. So this is what the data is going to look like. It's a matrix where one column shows us time, the other columns show us the concentrations that we measured of the various species. So I'm going to switch to COPASI, and I'm going to load a model, which is a simple chain reaction. It's basically 4 reactions that convert 3 species, A, B, and C. I can show you the diagram. By the way, if there are questions about what I just explained about parameter estimation, please unmute yourselves and go ahead, ask questions. So this is the diagram again. It's 4 reactions converting A into B into C. In this model, we have the reactions B of mass action. So we're only going to fit a few constants. And in this case, we have obtained some data, which is, as I showed here, something like this. You'll see in a moment. So parameter estimation has its own task here under the task menu. I highlight parameter estimation, and this is kind of the busiest window of COPASI. It has a lot of information here, so we're trying to go a little slow here on what these things are. First one is that you cannot do parameter estimation without data. So the first thing is data that you obtain in some way. Maybe you do the experiments, maybe your colleagues did the experiments, maybe someone who published a paper in 1936 did the experiments and you're recovering those data and using it. That's perfectly, all of these are examples of things that I have done, including the dates. So experimental data, you enter it here in this button, where it defines one file or a series of files that contain 1 or more experiments each. And these experiments then need to be mapped. The file, which I'm going to show you in a second, the actual file, it's a tab-separated file, which I've opened with a spreadsheet. And it looks exactly like what I showed on the other thing. So it has time, A, B, and C. This first column is just labels. And then it has the numbers. And it's a simple time course with time measured at regular intervals in this case. But it didn't have to be regular intervals. These numbers could be any time values. They should be, of course, in a sequence, in an ascending sequence. And the data for A, for B, and for C. So I have 1, 2, 3, 4 columns. When I load this file in COPASI, it will show me the 4 columns here. They're actually now displayed in rows, but they are corresponding to the columns of the data file. And COPASI is displaying here what the data file has in the headings. So if I had written something else here, it would appear the way it would be. In fact, I'm going to make those changes so that you will see. I'm going to call this clock rather than data, rather than time. So if I save the data file, and now I remove it from here, so I'm going to have to define everything from scratch. I'm going to choose the file that has my data, which is this one. And you see COPASI loaded it, and it shows me the headings here. So now it says clock. Now, the first thing I need to do, first of all, is check whether this is correct. First row is row number 1, last row is in row number 12. That's actually exactly correct. The first row is a header. I have a header in row 1. That's also correct. COPASI guessed this because it found that this row doesn't have numbers. So there are things there that are not numbers, so it must be headings. And it also figured out that there's a tab separating the data. If you had was a comma separated value, it would find a comma. You could specify a comma. It could be specified any other kind of character to separate data points. And so the next step is to tell it whether it's a steady state or a time course experiment. In this case, it's a time course experiment. Now, a time course experiment must have a column with time. It's impossible to fit time course data if no one measured time. So COPASI will not move on until we define that one of these columns is time. Now, as I had a file before, the column was called time, it would automatically discover that this should be the one. But because I called it clock, it doesn't know about that a clock measures time. So I'm going to have to say that this column here is not ignored, it's time. So I have 4 options. It's ignored, time, dependent, or independent. And dependent and independent I already described before. So that's time. And then what is A? Well, A is a dependent variable. Dependent because it changes. And in the model, its value is the outcome of a simulation. And in an experiment, it's the outcome of a measurement. So we don't set the value of A. We measure it or we run a simulation to find out what it would be, which is kind of what measuring is. So it's a dependent value. And as soon as I say dependent, COPASI wants me to find out what is this in my model? Is it a compartment? Is it a reaction? Is it a species? In this case, it is a species, and it's the transient concentration of a species. That is, it's the concentration a long time. So I have it here, transient concentrations. I expand this, and now I choose A. So it's mapped. This column is mapped to the variable that it has in the model. And I'm going to have to do the same with B and C, and I'm going to go a bit quicker because it's just the same. B is also dependent. It's also a species, transient concentration, and it's that one. And the same thing for C. Now, what you saw appearing here are these values in brackets on the column that says weight. And COPASI is already automatically finding out how to apply weights to the data such that they will be equivalent, that the time courses of C will be equivalent to the time course of A. And it turns out that A is larger than C. So what COPASI does is looks for what is the smallest of these 3 variables, and it's C. On average, it's the smallest. And that will not be multiplied by anything. That is the values that it will take. And then it finds what is the mean value of A and tries to make the mean value of A similar to the mean value of C. And that's the number it needs to multiply the values of A, both in the model and in the data, such that they become more or less have the same average than C, and the same thing for B. Now, just to bear with me, it's actually not doing the average, not the mean value, but it's doing the mean square of the values. If it was the mean, it would be like this, and the weightings would be slightly different. And the default is mean square, and we can talk about what the difference between mean square and mean later on, but they are not very different. As you can see, the numbers are not a lot different between one and the other. They're on the same time, on the same scale anyway. Okay, so we've defined our data. I'm going to press OK. We have defined one of the 3 important things for parameter estimation. The next one is the parameter values. So to fit the model, we must select some parameter values that we can change. If we cannot change anything in the model, then we're not going to fit anything either. So in this case, we're going to allow all the rate constants of the reactions. So the influx, it's actually a fixed rate, but it has a parameter V. The outflux, it's a mass action, has a parameter K. And then reaction 1 and reaction 2 also have parameters K. So what did we choose in parameter estimation was the rate of influx, the V, the value of K1 of the reaction outflux, the value of K1 of the reaction 1, and value of K1 of reaction 2. And they are currently within quite large limits, between 10 to the minus 6 and 10 to the 6. And their start values are some values that the model had. But I could also randomize them. By the way, each of these rows can be read here when you highlight it. So it's the exact same data that is written in that row, it's written here, but in a place where you can change it. This is where you would change if you wanted to change things. So if you highlight another one, they'll show another one. If you highlight several of them and you change something, it changes all of them. I'm going to put it back. And if you wanted to change their start values, you could highlight one and you could change it here, but if you highlight all of them, you can apply certain things to the all start values. And what you can apply is to initialize them to the value that you have in the model currently, to random value, or the value that the previous attempt at parameter estimation produced. Now we haven't run a previous one, so there's no current solution, but well, current solution is the same as model. That's basically what it is. So we're going to leave this. So we've defined two things, two of the three important things. One is the data. Second one is the parameters we want to fit. You don't always have to fit all the parameters. Perhaps you have information on one of them that you know what it should be, and you don't want to fit that, you leave it alone. Don't include it in this list. And then the final thing we need to do, which is down at the bottom here, is to select an algorithm for minimizing the sum of squares to fit the data. And here is where all the algorithms can be chosen. This one, called current solution statistics, it's actually a null algorithm. It's no algorithm at all. It's just going to run and measure the distance between the model and the data as the model is right now, without applying any changes to anything. So I can run that and show you where the data is. If I press the run button, it basically did all that measurement, and it showed me here, because I had already defined the plots, it shows me the measured values of A. These crosses are what the data that my file has. And this line, which is on a even totally different scale, as you can see, goes to 600, is what the model would produce for A. So this is really not a good fit at all, but this is where we're starting. Same thing for B. In this case, B, the model produces much lower value than the data. And finally, C, the data is a curve like that, and our model is doing something else. So this is not a good fit. It's what we have. And we're ready to run the parameter estimation. So we just pick one algorithm, and we can then run parameter estimation. Let me make this plot a little smaller. This one here on top is going to show us the sum of squares, which will be a number that will become smaller and smaller as we move along. So let's choose the first algorithm. Let's choose NL2solve. This is an algorithm that is basically based on derivatives as well. It's sometimes very efficient, but as you will see in this case, it's not the best one. So I'm just going to run it. So I chose the algorithm. For each algorithm, you will see this settings for the algorithm can be adjusted here. These are basically meta parameters, how the algorithms run. NL2solve doesn't really have any. The only one that it has is how many iterations, at how many iterations will it stop no matter what. If the model converges, it will stop before that, but if it hasn't converged after 2000 iterations, it will stop at that point. So you can make this larger if you're willing to wait longer. Of course, the algorithm may converge in 50, and therefore it would never run the 20,000. So all I have to do now is press the run button, and to my surprise now, this algorithm was really pretty good. You can see the progress of it here. This is the sum of squares before we even see the solution. This is the sum of squares, started at 100,000, and it started coming down very quickly with a few iterations of the model, and it came down to below 0.01. Now you can see the plot, and it's pretty good for B. See, the model is it's the solid line. It's very close to the data. And apparently also the same for A, although in this scale, maybe it's not. So let's look at just A alone so that we can auto-scale it back up. So it's also a pretty good fit. And then finally, C, which is on a much smaller scale. I have to switch off the others. It's also a very good fit. So in this case, I've solved my problem. This algorithm works very well. But we can try out the other algorithms and see whether they work or not as well. So it would be very easy. By the way, before we go there, you can now look at the results themselves. So what really matters is what is the value of the parameters, right? So if you expand here, you see result, and now you have some statistics. First one, this is just the overall fit. Gives you, this is the sum of squares, the weighted sum of squares. That's some statistics about it. How many data points you had, 33. How many function evaluations we ran. That means this algorithm had to do 105 simulations. So it went 105 times around that wheel before it got the parameter values small enough. This is just how long it took in CPU seconds. And that's how many simulations per second the algorithm ran. Now, if you come to parameters, this is what matters, right? So here are my 4 parameters. This is the lower boundary that I set for them. This is the upper boundary I set for them. This is the start values. So far, this is only information I've actually supplied. And this is the solutions. This is what the algorithm determined for these parameters such that the fit was this nice. And that's the value of one of the parameters, that's the value of another one, value of another one, value of the other one. And then over here, I have a coefficient of variation. This is basically, it quantifies how good is the solution. So the smallest the number here, the better. This is it's a standard deviation. Some people call it a relative standard deviation. It's a standard deviation of this fit, which is actually listed here, divided by the actual value and expressed as a percentage. So this parameter here has a coefficient of variation of about 2%. And that one has 1.6. And so even the worst one is still 8%, which is pretty good. You could also look at how, in this case, there's only one experiment, so there's not much to see there, but you can also figure out which of the 3 variables is better fit. So you also have data for each of the 3 variables, the objective value for each one of them, and etc. You can look at the correlations between the parameters. This is a correlation matrix showing you how one parameter is correlated with another, etc. Ideally, they should not be correlated, but it's impossible. In a model, they always will have correlations. So that's the solution. Any questions so far? Okay.
Hi,
so
I've got one question.
Yes.
Yeah, so what if we don't have enough information from either from experimentation or literature for few reaction constants? Means if we have 30 reactions to build a model, so if we have information for 20, let's say 20 reactions for their rate expressions, rest we don't have any other authentic information. Can we, any other way to estimate those reaction rates?
Well, you need some information, right? So this is the problem always. If you don't have experimental data or data that's you recovered from some paper, maybe they only have a plot, but you could use there are some software that you could use to digitize the plot and actually get estimates of those numbers, and use that. You can use that for parameter estimation. But if you have none of that, then this task parameter estimation is not useful. If you don't have data that you could adjust those parameters. By the way, the data is not on the parameters. Bear in mind here that the data we have is on the species, A, B, and C. That's what we measured. The parameters themselves, these 4 parameters, we don't have any data about them. What we have is data about A, B, and C. We are using this task to minimize, to guess the parameter values that best match our data. So I would say you're not looking for necessarily for the experiments that measure the parameters. You're looking for experiments where they measure the variables of your model. If you have that, and you have already values for 20 parameters and you have 30 parameters, you could try to fit the other 10. Now, it depends how much data you have and what kind of experiments, whether that fit will be successful or it will have a lot of uncertainty, right? So to get certainty, like in this one, I have very good data and I have really a model that fits the data, as you can see. So I could have very small standard deviations. But if you have no data at all, if there's no experiments, no measurements, then you cannot use parameter estimation. Then you have to do something else. For example, you could try to find out does the model change a lot when you change one of the parameters? So you can set values for them and then start changing one at a time and see how much effect they have on the model that you use the parameter scan, for example.
Okay.
But without
Thank you.
measurements, without experimental data, you cannot run parameter estimation.
Okay, thank you.
Any other questions? Okay, so let's look at what some other parameter would do. So what
Pedro,
other?
there was a hand raised. Theo, do you have a question?
Yes, it was just a specific thing about the function evaluations.
Okay.
Does that if you have multiple different experiments that say take place in different conditions, and so every run of one set of input parameters is actually sort of 3 different simulations, does the function evaluations count the different experiments as sort of 3 evaluations or 1 evaluation? Like what it's
Yeah.
a bit. I just wondered.
So what the software will do is create a very large, very long sum of squares of residuals. And the question is how it weighs them, right? Because if in some experiments you have values that are much different than other experiments, you may or may not want to normalize everything. So in this case, we actually have this tick as normalized weights per experiment. So these weights were normalized for this experiment. It tries to have all 3 variables weigh the same in this experiment. If it had another experiment, it will find the weights to make those all similar. If I don't have this normalized per experiment, then they are all normalized against all of the data towards absolutely all of the data, all the experiments.
Right, okay.
Correct me if I'm wrong here, because
Nope, it's one function evaluation because all experimental data is combined into one weighted sum of squares.
Yeah.
And so we do multiple simulation or steady state calculations. At the end, this is one parameter set evaluated, and that is called as a function evaluation.
Yeah.
It's from the viewpoint of the objective function.
Okay.
So if you have 15 experiments that require us to run 15 time courses, one function evaluation is those 15 time courses.
Okay.
When I say here, when this result says that it ran 105 function evaluations, in this case, it's really 105 time courses because I only have one. But in the next one, I'm going to show with, in fact, maybe we should do that since time is coming quickly.
Thank you very much.
I'm going to show another example where you will see this more clearly. Okay, so I'm going to load now another file, which is also feeding data, but this one has more than one experiment. So this is actually a very simple enzyme kinetics parameter estimation. So it's data from one time course using enzyme kinetics. So what we have is the Michaelis-Menten mechanism here, substrate plus enzyme giving the complex going to enzyme plus product. And we have rate constants for each one of these. These are both, the first one is reversible, the other one is irreversible. So we have 3 constants to fit. So if I go to parameter estimation and I show you experimental data, in this case, I have one file that has several experiments. It has 5 experiments. And each experiment contains the initial concentration of substrate, time, and an absorbance. Now, an absorbance, for those of you who are not biologists or biochemists, absorbance is it's one way of measuring concentrations. You have a molecule that absorbs light in a certain wavelength, and with a specific device, you can measure how much light was absorbed in that frequency, and that gives you a number that's proportional to the concentration. In this model, we actually included a function in the global quantities that calculates the absorbance. And what is the absorbance? It's the concentration of a certain molecule, in this case P, times the coefficient, which is called the molar absorptivity, and plus an offset. The offset is because the experiments, the measurement drifts. And so you always have to do is to put a solution that has zero concentration of that molecule and set it to zero, but that drifts along the day. So we included it here because we are going to want to correct for it. Otherwise, I could just leave it at zero, right? So if this offset is properly zero, then this would just be the concentration times the coefficient of absorptivity, the molar absorptivity. Now, the coefficient is a parameter that I have here. Now, in this case, we knew what the parameter was. And the offset, we started at zero, but we don't know. Maybe in some experiments, it's not zero. So this way, we can fit the absorbance directly. We don't have to fit P, because we have data from the spectrophotometer. We don't have concentrations. Now, of course, we could use Excel and calculate them using exactly the same formula or the inverse of this formula, but we're going to use directly the absorbances. So we're going to try and fit this function here, absorbance. So in my experimental data, this line is the absorbance. Essentially, it's the concentration. It's something proportional to the concentration of P. So by changing the parameter values, we still are changing P. But the one thing that's different in this case is that we have an extra thing, which is this initial concentration of the substrate, which is an independent item. Why is it independent? It's the initial concentration. It is a given. It's something that you made or your experimental colleague made in a solution to start the reaction. They actually made substrate in 10 millimolar. And then in another test tube, they made initial substrate concentration of 5 millimolar. So we know it's 5 and 10 millimolar from the experiment. So the data set in this case has the initial concentration for this time course that starts here. We have the initial concentration of substrate. This is still a one-time course. Then there's an empty line. That's the next experiment, another time course. And this is now the concentration of the substrate at that experiment. And this is another one, another experiment, another initial concentration. Again, time and the absorbances. So that already shows that we don't have to fit exactly the variables of our model. We can fit a function of them. But we have several experiments in this case. So one function evaluation is going to be 5 time courses, actually. So let's try and fit this data again. I'm going to just press the run button. Levenberg Marquardt is selected. I'm going to use it. And I've got a fit. I've got a lot of data here. I have 2 plots, 3 plots. Is there a question? Okay. No, I thought I had heard a question. I have 3 plots. One is the progress of fit, which is just the sum of squares going down in time, right? The other one is the model versus the data. The data are the crosses and the model is the continuous line. And there I have 5 experiments. And then finally, I plot the residuals. That is the difference between the model and the data. And as you can see here right away, this red, the experiment 1, the one that doesn't have a number, has much smaller residuals than experiment 4. Experiment 4 has the largest residuals. And that's because experiment 4 is this one, has the highest absorbances. And so, of course, this distance is quite large. It's much larger than actually the value of absorbance in the experiment with the lowest concentration. And this, again, demonstrates why we need to scale things. So if I have to actually remove the data to show you the lowest experiments. And you see this one, the fit is not very good because the data goes there and the model is just all above it. And the hint why this is happening is that the model thinks that absorbance should be 0, the offset is 0, but the real offset is much smaller than 0. It's probably somewhere around here. It's a negative value. So somebody didn't adjust their spectrophotometer, or it just drifted. They adjusted it in the beginning of the day, but by the time they did this experiment, here it's the opposite effect. Here we are starting to getting closer. Now we have a good fit already. I mean, it's a little bit, there's a little bit of bias down here. The model is always underneath the data, but over there it's already not so bad. And the final experiment has a perfect fit. So this is a good example of how the noise in one larger noise experiment with a larger noise will always determine the fit. So we could do a few things to improve this model. One of them is to add another parameter, which is the offset. So now the offset may be, but we don't want it that large. So the offset is going to be a small value. Maybe, well, we saw that, right? So we can look at the data and try to kind of visualize what would be. So you see this one is down to minus, well, maybe it's minus 0.06. Let's use minus 0.06 as the minus 0.8. Okay. That's the minimum value I'm going to put. And the maximum value, maybe we look at another experiment. Well, it's close to below 0.2. So let's use that's the
upper bound.
0.15. So this may be correct or not. So let's run the model again. Again, looking at this experiment tells us nothing because this one is always very good fit. So we want to look at the lowest one. But it's worse than it was before. Maybe in one of the others it got better. This one I think got a little better. That one got much better already. So it improved things a little bit, but it didn't do the job. And the reason why it didn't do the job is because if you look here, the experiments all have different offsets. If you try to extrapolate this to times 0, they are all in different places. So the offset was drifting as people did their experiments. So we want to fit the offset, but we want to allow it to be different in each experiment. And this is possible to be done with any parameter, actually, but we don't think that the reaction itself changed. The parameters, the inherent parameters of the kinetics didn't change just because we did one at 2 p.m. and we did the other experiment at 3 p.m., but only the offset. So we're going to highlight offset, and we're going to say duplicate for each experiment. Should be called multiply for each experiment. But
yeah.
So now we have 5 different offsets, one offset for each experiment, and now they can be fit independently. They can have different values. So I'm going to run this again, and I will hope that the fits are much better, but they still are not. And
That's
now
weird.
this may be because Levenberg-Marquardt is not doing the best job. So let's look at other algorithms. By the way, we now have 7 parameters, right? So it's the 2 kinetic constants that we were fitting, plus 5 initial offsets. So I'm going to use the particle swarm. Particle swarm is a fancy algorithm. As I said, it has many, in this case, 50 candidate solutions, and they all are moving in certain random directions, but biased by the other solutions. And the better the solutions, the more bias they give to the others. So as soon as one starts getting better, pulls the others in that direction, but they're still kind of going in random directions. There's always a random component, unless one of them becomes very, very, very good, and then it starts pulling all the others in the same direction. So this takes a little longer. By the way, when it takes a little longer, we can look at the plot of the sum of squares, which I don't know what happened to it.
Pedro, I think your offsets were both positive. The upper one is a minimal value for offset needs to be negative.
Okay, so I'm going to stop. Stefan found out the problem.
So Jim Schaff found out.
So the offset, the lower bound is not 0.08, it's minus 0.08. right? That's why it was not allowing. By the way, this also shows one of the common pitfalls. It's always good to think and cross-check what you did, because obviously, if this value is positive, then the offset was even larger than 0, always. And that's, of course, would never fit this experiment. So let me try again. And I'll use the particle swarm anyway. So when an algorithm takes longer than just a couple of seconds, you get this window, which is showing you the value of the sum of squares, which is this number, and how many function evaluations. Now, this is function evaluations. This multiply that by the number of time courses. So the number of simulations, it's actually that times 5, which just shows that modern computers can run a lot of stuff, even on a single Xeon CPU, which we're running here. I'm not sure if this solved the problem or not. I stopped it, so that's one thing you can do. You can always stop. Haha, problem solved. Now this fits the data fairly well. I mean, okay, maybe not completely correctly here in the offset, but it's definitely much better than it was before. And what about the others? Same thing with the others. Of course, the largest one is always good. The largest one was determining all the fit anyway, so that one is going to be the same. Oops, sorry, I'm clicking on the wrong things. So now I've finally managed to have a proper fit, and I did not have to go back to my colleague and tell him that the experiment was not done correctly, that he should have set to 0. I actually was able to compensate for that. And in fact, I have now an estimate of what should be the offsets. Here are the estimates of the offsets. And of course, the estimates of the parameters, the kinetic parameters, which is really what we wanted to obtain. And their coefficients of variation, which again are very good, 1 and 7%. So these are very, very good. We also have the correlation matrix. Again, correlation values are actually pretty good. They're basically 0 among the offsets, which just says that they're not correlated. Of course, they're not 0 between the two kinetic constants because they are in a coupled system of ODEs. So I think I'm going to stop here and ask if anybody has any questions about parameter estimation.
Just maybe one point. You mentioned parameter sets this morning. And
okay, so as Stefan said, in the morning I mentioned parameter sets, and you can automatically create parameter sets when you run a parameter estimation. And you do that by clicking this here. If you have this set, create parameter sets. If I'm going to run, let me use a different algorithm now because I just want to show different algorithms. Genetic algorithm is also usually very good. I'm going to just do 500 and maybe 30 individuals. I'm going to run. So when this parameter estimation is over, COPASI will automatically put those parameters in the parameter set.
Actually 5.
Yes, 5 parameter sets, 1 per each of the experiments, because of course they're different. So only the last one is in the model. The only difference between them is, of course, in the offset, because the kinetic constants have to be the same for each model. The kinetic constants don't change, they're always the same, but the offsets are different. That's why
offsets in initials, offset in initial states.
Yeah, offset in initial states, of course. Yes. But those were given in the data file. So we created automatically parameter sets. Now, if you don't want to create them automatically, because of course you may run this many times, and if you run the problem many, many different times, you don't want to be creating that many parameter sets. So now I have another 6, right? And they get, if you do the automatic, they get labeled by the time you run them. So now I have 6. So, you know, this second time I estimated 111,754. Previous time was 109. So they're slightly different parameter estimates, always 14. So that already shows you some variability. if you do more than one. But you may not want to create so many parameter sets. If you don't want to do that, you can just run. Let's run a different one now. And at the end of that run, again, you may want to stop when you think that you're converged. So I'm going to stop it. You press the stop button. Now what you do is you go to results. And you have to update the model. That is, you press this button to update the model. That will change the parameter values on the reactions. We'll make them what they were estimated in the parameter values. So we go result, update model. And it's going to ask us update to which experiment, because of course they have different values. Let's say for the first one, the kinetic constants are the same. And now in the model or the parameter overview, here you could store as a parameter set. Let's imagine this was the best one. So now that way I created just one by one. So maybe you tried, you were running this maybe 20 times or whatever, and you don't want to have those 20 parameter sets multiplied by the number of reactions stored. You want just one. And so this way you store just one parameter set. The values that matter are, of course, these two. The offset is set to whatever experiment I picked, but of course, in different experiments, there are different offsets. Any questions?
Yeah, and another comment how to create it. You can at first run your parameter estimation with your favorite algorithm without creating parameter sets on. And then you run current solution statistics with create parameter sets on.
That's probably a better way. Yeah. If you do this, then it just runs with the current solution. The other thing you can do is click here on update model. And that would automatically do what I did by pressing that button, which is once the parameter estimation finishes, the values get copied to the actual model here. And that means that the next time you start, you will start with those values already. So you can run one algorithm and then refine the solution with another algorithm if you want to. So let's see, there are some questions on the chat. Okay, so there was a question about the offsets applied to the model or the data. Of course, it's the model, because offset is only one thing that appears in my model. It's part of this equation for absorbance. In the data, you would actually change the knob in the spectrophotometer to adjust the zero. That's the parameter on the experiment you could do. Is there a way of calculating the area under the curve of a species time course and then using that to fit in parameter estimation? Stefan, do you know? I think we can do that, right?
Yes, you would have to integrate the curve, which you could, because that's just another ODE, isn't it?
Yeah.
That's a handmade ODE for the summation of the species. So you can create an ODE which has the value of the species as a derivative.
Yeah. So I think this question was asked by Theo. You're in one of the groups, right?
Yeah.
So we
Yes.
can discuss that in the group. We can do that in the hands-on part.
I haven't done it, but it's doable.
We believe it's possible.
Excellent.
So we
Thank
can
you.
play around with that. Any other questions? Otherwise, I'm at the end of my time. Yeah, so there was a question earlier. When I say we change the parameters, does the application iterate over those values? It's, of course, the application. You probably already saw that. I mean, question was asked early on. Yes, these algorithms, the different algorithms have different strategies to iterate over the parameter values, but it's all automatic. Each one of them does it in a different way, but they all do it in an automatic way. So anyone that you pick will have basically looked at all the parameter values. Okay, I think I'm going to stop.